Okay, so today for the tutorial, I'd like to do this example. This example, it's not difficult, but the level of analysis that you have to do for this question is, I'll say, medium to high. Okay, you have to sit back and see what is going on. Okay, so that's why I picked this question. Okay, and if you were to look at this question, it is very similar to the last question of your homework. So the last question usually is the hardest. Okay, so called the hardest. Okay, so I'd like to do this question. All right. So there's a vertical force P. It's applied at point C, located on the axis of symmetry of the cross section of the short column. Determine the range of values of Y for which tensile stresses do not occur in the column. All right, so it is a very interesting question. Okay, they want us to determine the value of Y for which we only see compressive stress. Okay, we only observe compressive stress, right? So if you look at this problem, what you see that we have to know, is this problem, okay? So we have to ask ourselves, is the problem, so the problem, as you can see, the problem is eccentric, symmetrical, loading, okay? And why is eccentric? Because we have axial load, okay? Eccentric because we have both axial and bending load. Axis symmetry is because along the y axis, okay, along the y axis, right, the stresses on the left is equal to the right. So if I will call this left and this is right, okay, so stresses on the left and right have the same magnitude. So that's why it's classified under symmetry. Okay, so we know that once we identify there is an eccentric symmetrical loading, we are going to calculate stresses in Y, right? So stresses in Z. What do you mean by Y? And I'll tell you why is it Z. Stresses in Z. So this will be equal to PZ divided by area, right? And we know it's going through compression minus, right? Then this is plus or minus moment about X over IXX multiplied by Y. Okay, so that is the rule of the equation. Okay, so if you look at this structure, right, so what we want to determine is the Y. Now, at any time and anywhere, if you don't understand anything I'm saying, or if I'm going too fast, please stop me to repeat. I will certainly do so. Okay, so now we have to construct our transformation. Okay, we have to construct our transformation first. So I got a bigger diagram that I'm going to use. Copy. Okay, so I'm going to, right. So we have to construct our transformation. So we know that this is our Z using right hand rule. This is our X. And over here, this is our Y. Okay. So the first thing we have to determine is we have to find, okay? We have to find, but before we find anything, we have to analyze first, okay? So the question tells us, give us condition, okay? So condition that they said, that they gave us is stress Z. Right now, you know why Z, because we're calculating in the Z direction, right? At point A, and stress Z at point B, right, must be compression only, right? So we know in most of our cases in that we have learned in bending, right? We have a neutral axis, right? At the we have a neutral axis because one side of the neutral axis you have tensile stress, the other side compressive stress. But for this problem, okay, they don't want any tensile. Okay, they say that they say that what? You look at the problem, which tensile stress do not occur in the column. So they only want it to be compression. Some of you will ask me, Eugene, in what cases is this possible, or in what situation where you only want compression, you don't want tension? Anyone know that any situation of a structure that you only want compression rather than tension? Anyone? Can you tell me what material would be most suitable for such an analysis? Anyone want to make a guess? No. Brittle material. Okay, brittle material like concrete. Concrete is only good in compression, not reinforced, but just pure concrete. Okay, is very good in compression, but in tension it is very bad. Okay, so example of material. Okay, that can only withstand compressive stresses. So it's usually brittle material. Okay, brittle material, so glass, okay, concrete, okay, etc. Okay. So in this case, we were asked to find out we were told that stress Z at point A and stress Z at point B has to be compression. Okay. By no means we're allowed tension. Okay. So if we look at our function now, if we look at our equation, okay. So the equation, like I wrote earlier, is stress Z is equal to Pz minus Pz divided by A, right? Then this will have we will have as plus minus mx over ixx multiplied by y. Why is it x? Okay, because the moment can be in this direction. Hold on, can be in this direction or the other direction. So these are in the axis of rotation is about the what? X-axis. Okay, the axis of rotation. So if I'm going to draw the axis of rotation, this is the axis of rotation. It's parallel to your x-axis. Okay, so that's why it's moment about x. So with the arrow that I've just drawn, right, there will be a case when it is depending on where the centroid is, right? A can be compression, okay. B can be tension, or B can be tension. A can be compression. But we are going to adjust the y distance. Okay, we're not going to adjust. We're going to find the limits of the y distance such that point A and point B has to be compression. Okay. So if I were to write this formula or expand this formula further, so this will be equal to minus PZ over A, right? So I think this, calling it Y, I'll call it Y squigger. Okay, Y squigger. So Y squigger is the point or the distance from the centroid. Okay, right? So over here you have PZ over A, right? Then the moment, right, is, oh, sorry, I'm going to call this Y, my bad. Okay, this Y and this Y are not the same. Okay, I want you all to see that. Okay, so plus or minus PZ multiplied by Y squigger, right? Distance from the centroid, right? Divide by IZZ multiplied by Y. Okay. So this distance from the centroid, Y squigger, right? If I were to draw a diagram here, it can be in this direction. Okay, it can be this direction, Y squigger, or it can be in the opposite direction, depending on what we want to find later on. Okay, depending on what we want to find later on. Right. So what we can see over here, right? What we can see over here, looking at this equation, okay, looking at this equation, this entire term over here, right? This entire term over here is a constant. The area will not change. The cross-sectional area will not change. The axial load along the z-axis will not change. Okay. Likewise, PZ will not change, constant. IZZ will not change, right? Y over here is dependent on the point of analysis relative to the centroid. Okay. Now I have some issue calling this Y, right? I'm going to get rid of this. Okay, I'm going to change this. I'm going to call this value alpha. Okay, for this case, because where you see too many Y, like Eugene Y, right? It's too many Y, right? So I'm going to change this point. I'm going to call this alpha. I'm going to change this to alpha. Okay. So now, before we go on, we have to determine what our constant are. Okay. So in this question, we are not given any PZ value at all. Okay. PZ is just a variable. Okay, fine. Okay, it's just a variable. We move on. If you look at the question, as I said, they did not tell us what is the vertical force value. They just call it P. Okay, so we call ours, this will be equal to PZ. Right, fine. We have no problem with that. Okay, so the next thing is we're going to find our, yes.
Okay, so how'd you make in the first part you had it as IXX and now you made it IZZ. How'd you do that?
So if you look at the moment is going, the PZ is going to induce a moment about the ZX axis, yes or no?
Yeah.
Right? So if it's MX, you have to divide by IXX multiplied by Y.
Yeah.
Does that make sense now?
No, but in the next part you made it IZZ. How'd you do that? In the next line.
Oh yeah. What I say is yeah, what I say and what I write is different. Sorry.
Oh, okay. Never mind, I got it. All right, thank you.
You got 1 point.